Thanks for joining me today. My name is Rob Bayliss, and I'm here to talk about load testing, and I'm going to talk about it in the context of a case study on some load testing that we did for the state of New Jersey for their unemployment modernization project. Just a quick note on me. I'm a civic technologist. I've been in civic technology for 10 or so years, developing websites for, 15 or 20 overall. And my sort of like interests are mainly in SRE, so DevOps, automation, performance, that kind of thing. I'm also a principal at Mighty Acorn Digital. We're a small digital agency that's focused on bringing sort of like best practices in DevOps and release pipelines and automated testing to state and local government projects. I do this work because I see the web as a force for good. I think open standards are a really powerful concept, and I think it has the ability to improve lives. Bringing that to government technology is a worthy goal. I'm passionate about open standards and performance and all the things that I said. I think this case study is kind of important because I think there's a big need for our government services to be resilient to emergencies. And so a lot of what I'm going to talk about today is sort of like in the specter of COVID. And COVID really proved that government services, like technology services, were not up to the task. And so there's no way to fix that other than to plan for it. And I'm hoping that this session can sort of like plant the seed of planning so that people can like get ahead of the next emergency that happens. So I really want to promote readiness for the like real world things that could happen, and also share some practical insights. All right, so I'm going to tell a story today, and it all starts at COVID-19. We can see here a news story from NPR. Unemployment websites are crashing across the country. So I think we probably all remember some version of this right around March of 2020. State government websites just got inundated with traffic of people either looking to apply for unemployment as their jobs disappeared temporarily, or we're just looking for information from the government. And it hit unemployment particularly hard. So this is a graph showing like unemployment rates over time, and you can see that giant spike. This is what in SRE circles we would refer to as like a black swan event. This is sort of the nightmare, right? Like you get relatively consistent traffic over time, and then all of a sudden you just have this massive spike. And so there's really no way to like predict that this is coming. You just have to be ready for it and ready to scale when it happens. So just switching gears for a second, I want to read out this statement that so the New Jersey Unemployment Office has a modernization effort, and that's driven by this New Jersey Office of Innovation. And this is the problem statement for sort of like the UI Unemployment Modernization Project. As the COVID-19 pandemic upended lives and the economy, millions of New Jerseyans were suddenly left unemployed. The unprecedented flood of applications to the state's unemployment insurance system significantly strained a legacy system that had been underinvested in for decades. Complicated application language, incompatibility with mobile devices, and ever-changing federal guidelines compounded the challenge of a massive increase in application volume. Residents were frustrated by delays and confused by the process, while state employees struggled to do their work within an inefficient system. So not only did we have this situation where the the systems crashed the moment that they got too much traffic, but you also had this sort of like bigger problem of these applications that were not developed for the scale that we're operating at today. And we had human problems as well. And so the UI modernization project is really about solving all of that. And I just want to give a quick overview of that project. It got rolling in 2022. And it's focused on modernizing a really complex system. I'll show you an architectural diagram in just a minute, just illustrating the complexity. But the whole system is built around a mainframe that's been in service for quite a while. I don't know the exact date that was set up. The project team has grown to over 100 people. So we have people from multiple vendors and state organizations working on it. And Nava PBC is the prime, and they brought us, Mighty Acorn Digital, in 2023 to help out with automated testing. So that's sort of the backdrop for this project. And this is that architectural diagram that I mentioned. You're not going to be able to read this. Don't worry about it. What you can see here is just a lot of different systems. And depending on how you count them, there are like 6 to 12 different applications in play here, forming the unemployment system. And each one of those has its own data store, so there are multiple data stores in use. Communication between these systems is completely inconsistent. And all of it is going to flow back to the mainframe, which is sort of this central piece here. And apart from the mainframe, which is written on COBOL and really hasn't been touched in a while, development on these systems is nearly constant. So as we modernize all these different pieces, it's going to be shifting and growing and changing. And you can imagine that makes a really complicated landscape in order to test, because you have so much changing and so many systems in play. There's not a single sort of strategy for testing that covers it all. You need multiple. The other thing that's going on here that makes this difficult is the stakes are very high, right? This is a critical application for the state. People are depending on it. There's zero tolerance for service disruption. So, it's very important that this service keep working. And it's also one of the first UI modernization. When I say UI, what I mean is unemployment insurance. It's one of the first UI modernization initiatives following COVID-19, so it's got a lot of eyes on it across the country, people watching how this goes. And obviously, as I mentioned, with so much ongoing development, things do break. There's a lot changing all at once. And so as we came onto the project, our mandate was to identify, reduce, and mitigate risk. And one of the biggest risks that we saw was high traffic. So, given that that's our mandate, our job is to test for and find those unintended consequences or regressions as they happen. And the approach that we've taken here is multi-pronged. We have end-to-end tests running, testing all the critical functionality, and these end-to-end tests are going to go sort of like spider web out across all those different systems that comprise the UI system. That's one piece of the puzzle. At lower levels of testing, is anybody familiar with this testing pyramid? Have you seen this before? A few people at least? All right. Yeah, so the idea here is, this testing pyramid has the most amount of test coverage at the bottom, so unit tests. So unit tests will be written for each component of this system, and the project teams that are working on them will write the unit tests. There will be integration tests on how those components are interacting with each other. And then at the highest level, there's end-to-end tests that test all of the pieces working together to make sure all the pipes are hooked up. And so Mighty Acorn, our job is to make sure, A, that this whole pyramid is intact, but B, to make sure that we're writing and covering that sort of end-to-end journey so that we cover the functionality. So that's prong number one. Prong number 2 is a comprehensive program to help identify risk at the level of the change where it's introduced. And prong number 3 is load testing for anything that involves or introduces a stability or performance risk. So if during the proposal of a change, like a pull request, it's flagged that it might involve some level of stability risk, we're going to run load testing on it. How many folks in the audience have done load testing before? Cool. All right. There's a few. So for anyone who hasn't, the sort of like rough concept here is, imagine you just built a bridge and you want to know, does it support the number of people that are going to be walking across it? So you're not going to test that by sending people across the bridge and just seeing if it falls down. You're going to add weight to it gradually and see, like, can it support the amount of weight that I expect to be on here? And so that's what we're doing with load testing, is we're simulating traffic going into the website. And we expect that it's going to be able to hold up to, the normal amount of traffic. We also expect that it's going to be able to support the peak amount of traffic that we expect to go through it, so like a really busy day. And we also test to find out where it falls down, where it starts to break. So that we have, that level in mind as traffic increases, and we know that when we hit that level, things are expected to get weird. Okay, so that is load testing. And so fast forward to, we know that we need to implement load testing on this program. And the first thing that we did is we tried a tool called K6. K6 is an open source tool put out by Grafana, and it is a tool that's written in Go. What you can see on your screen here is we're navigating to the unemployment website, just the homepage, and we're seeing at the bottom it's called the waterfall of requests. So it's the network tab of the developer tools. And we can see that there are, a couple dozen requests that are made on visiting the homepage. And so our first shot at this was go to each page of the site, find out what requests are made, and then simulate making those requests one by one. And so you can imagine this application is actually quite complicated. I'll show you a video of kind of walking through it in just a second. Actually, I'll just show that now. So there's many pages to filling out this form. This is a recording of one of our end-to-end tests in action. And you can see that, there may be 20, 30 pages to this application. So take the number of requests made on the homepage and then multiply that by 20, 30 pages, and you know the number of requests that we're going to need to make. So it's a bit daunting, but okay, so we decided we're going to try this approach. We're just going to sort of list out all those requests. Okay, so we implemented that. And what you can see here is just a snippet of code kind of demonstrating that. You can see each line is a single HTTP request. We have the GET of the homepage. We have the GET of the claim start page. We send out a request to start an application, and we get back application ID, which we then pass in on further requests made down the line. So there's a dynamic aspect to this. So this was complicated, but we did it. And we put it all together into a single script. This is written in, looks like JavaScript. It is kind of JavaScript, except it gets compiled down to Go before it gets run. And each time this function gets called is one iteration through that process that I was showing earlier where we submit an unemployment claim. So we put that together. We set concurrency for it. So we said this amount of traffic, and we put it into an AWS code build job and kicked it off. Great. It was actually successful. Of course, we had to, it wasn't quite as fast as that, but we did get it running, and what you can see here is some CloudWatch graphs showing the different metrics that we were watching on this first test. Starting from the top left, you can see the response time, and that's largely flat except for that one kind of weird spike in the middle. Not sure what was going on there, but that topped out around less than half a second, so I'm not super concerned with it. You can see in the second graph from the top left, you see the number of requests, and that ramps up for 10 minutes and then spends 20 minutes at a consistent level, and then immediately ramps down. And then the last graph on your right there, on the top right, is 500 errors. And so that's responses from the server that are 500 coded. So those are server error responses. And we had a few of those during that first test. But overall, things are looking okay. You know, this is not a super unhealthy system. So anyway, we had K6, and it was working. A couple weeks later, we noticed we were just doing some manual testing on some other feature, and we noticed a new request in the request waterfall. So all of a sudden, we had this request to API endpoint for maintenance. And what this was is there was a feature request that came through that we'd be able to put the application in maintenance mode so that, you know, it would basically like pause things so people could not enter new applications when we were in maintenance. And so, great, that feature got developed and it came through, but we on the testing team didn't actually catch this issue. And we didn't catch the feature being introduced, and so we didn't know to put this maintenance mode request into our sort of like waterfall of requests that we were making. And this really exposed a problem for us because this request was being made on every single page view. So potentially a lot of requests that they're adding to each like iteration through the intake form. So obviously this is a problem. We were testing the HTTP requests that we thought should be there, not the requests that were actually being made by the browser. And this is a pretty common problem in load testing, I think, which is that traditional load testing really focuses on this protocol level load testing where, you know, it's very focused on make one request, get one response. But it doesn't account for modern web applications that are issuing, you know, dozens of requests at a time to different endpoints. It doesn't account for things like an application that may be rendered either on the server side or in the client side and may render differently accordingly. So as we started to try and figure out how to solve this problem, we had an idea, which is, all right, what if we use the browser for this? And this is kind of a crazy idea, kind of not a crazy idea. You know, we were already invested in Playwright, which is an end-to-end test tool, or a browser automation tool, I should say, that has an end-to-end test framework built into it. We were using that for our end-to-end tests. So we already had sort of a code investment in Playwright. And what we realized is we could reuse that foundation and it would give us test coverage that would be aligned with, you know, real user flows that are going through the application. And it would be done in the browser in a way that like we wouldn't be missing requests. So if someone made a change that introduced another HTTP request, we would just be testing the web page. We wouldn't be testing the list of requests that was there 3 weeks ago. And we weren't alone in this conclusion. Right around the time that we started to have this idea, K6 and Artillery, which are, you know, both open source load testing tools, released support for browser-based load testing using Playwright. And Artillery had one clear advantage for us. K6 compiled down to Go code, and consequently, the APIs behind that were different from traditional Playwright code that we were writing, whereas Artillery was a JavaScript-based tool that would actually like share the same APIs. And so this was a clear choice for us. We had to go with Artillery because it allowed us to reuse that same exact code. And what I mean by that is, if we call them page object models, and this is a bit hard to read, I think, but this is a test that sort of does the same thing that we saw in K6, but it's a lot more semantic. You can see that we are creating a new portal homepage class. We await homepage.start or restart claim. Then we fill to review. And so it's like, we're telling our page object models like what we need them to do. And the page object models behind the scenes know how to translate that into button clicks in a browser. And I want to be very clear about that because it is actually a browser opening and then clicking on a button, going to a URL, like doing all the things that a user would do. So anyway, filling all the form fields, it's pretty incredible how it does it. And so what this does, aside from solving our sort of like code maintainability problem, we ended up putting ourselves in the spot where we have tests that actually act and think like users. They are mimicking real user interactions. They're looking for buttons in the same way that users do. And the consequence here is we stopped focusing on HTTP requests, and we started focusing on whether the interaction that we're trying to test, the submission of an entire unemployment claim, could be executed or not. So the user journey success rate. So this also allowed us to do some cool things like, in some places in our application, the application would retry requests when they failed. And so that's not something that we were getting in K6. We weren't able to sort of like mimic that behavior easily. But since we were driving a browser, we didn't care that the request was failing for some weird reason, or maybe it was overloaded. But it doesn't really matter. As long as it's not affecting users, it can fail all at once. Likewise, you might have some single critical request in the path somewhere that if it fails, it's going to stop the entire user journey. And so again, we're not focused on individual request sort of like metrics. We're focused on user journey success rate. Cool. And so what we can see here, I'm just going to sort of like break this down. On the right, when we run our load tests, we often have multiple components. So we might have claim intake, which is the test that have been talking about so far, running alongside visits to the unemployment homepage. And we run these tests simultaneously to sort of like simulate different types of traffic that we know are out there. And so we can see that for the claim intake test, we attempted 934 iterations. So that would be journeys through the intake form. 932 were successful, 2 failed, and so that gives us a 99.8% success rate. So that's what I mean by journey success rate. So what that really means is if we have 934 real people that try and submit this application in a 30-minute period, which was the duration of our test, we can expect that 99.8% of those people will be successful in what they do. We do measure 500 errors seen during the test, and so I think one interesting thing to look at there is we had 8 500 errors, but that didn't correspond with 8 failed iterations. And so that's just an illustration of how that like user journey success rate is really what matters for us. And obviously you can see that the homepage metrics are a lot higher. On the left here, you can see the number of HTTP requests. This is the output from Artillery, which is the tool that we switched to. You can see that there are 333,000 HTTP requests made over the duration of this 30-minute test. And I suspect that this was from only the claim intake side. So we had another test running alongside it that had a similar volume. And so there's a ton of traffic going in here. But again, we don't have to worry about like individual request level stuff. We're just doing the browser stuff, and all that stuff happens in the background. And a couple more things I want to focus on with the artillery output on the left. You can see the CLS, or cumulative layout shift. FCP is first contentful paint. And if you're a performance enthusiast, you'll probably recognize these things as front-end performance metrics. And that's right. If you're using a browser, you are able to collect things from the front end as well. And while we don't do a lot with these in our particular use case, you could definitely form a whole practice here around making sure that not only is your back end performant, but your users are continuing to see a good experience. Cool, and the last thing I want to point out here is kind of in the bottom left of the K6 artillery output is the session length. And so this is the amount of time it took to go through each iteration. And we can see a min, max, mean, and then P95 and P99 metrics for those. And those P95 and P99 metrics are ones that we're really focused on as well, because those are the 95th and 99th percentile, accordingly, of time it takes for a single iteration. And because we're doing this in an automated way, like no human is going to go through this test in, this must be the homepage one, because they got through this. 99% of our test iterations completed in 4 seconds, 4.5. One thing I want to just point out is a healthy response time graph during a load test is going to be flat. And so you can see on that left graph, it's pretty much just, there's some small spikes, but pretty much just flat across. Now let's look at this test on the right. So this is a different test. This is we call this a breakpoint test, and this is where we're trying to find the point at which the application starts to fall apart. So in that bridge metaphor, it's like, where we were driving trucks over it until it starts to crumble. And we can see with that red arrow, the point at which it fell apart, and you can see the difference in the request graphs. They're totally different scales. The top number for the graph on the right is 2 seconds. The top number for the graph on the left is 400 milliseconds. But you can see that what we see when the application starts to break down is almost like hockey stick growth. Things start to bottle up and really what's it called? Just requests pile up and they're not able to be completed in time, and then that in turn slows down the ones behind it, and it just gets bad. So anyway, that mark at 405, it doesn't look that bad, but that's the point where we start to go over 1 second of response time, which is our SLA. So yeah, again, we were able to get this running, and we were able to get K6 running up to the point where we were able to make the application fall over. We didn't quite get to COVID loads with this breakpoint test. And just to sort of put this in perspective, our normal traffic volume is relatively low. Say I don't actually have the numbers for what we go up to here, but normal traffic volume is a 1 out of 5, and then COVID would be a 5 out of 5 traffic volume. And our breakpoint tests went up to 4 out of 5. So we were able to validate that we got pretty close to COVID numbers just using browser-based load testing. So we definitely validated the scale of this thing and the fact that we could scale it up to a large amount. And again, this was a much, much more maintainable way to code for us. Okay, so I want to kind of stop and give technical and kind of business takeaways here, because I think this is maybe the most interesting part. So I think modern applications are complex beasts. They're definitely, like, at least in the applications that we're working on, we don't have just like a web page that shows some information. We have interdependent pages. We have dependencies between sort of like things that happen in the system. And so it's not enough just to like, if you've ever used like JMeter, which is a load testing tool that is sort of like traditional, it's very good at issuing a single request and getting a single response. That's not very useful when you have an API endpoint that like needs you to have first created some data, and then like later on there's an API endpoint that depends on that second one. So where you have those sorts of interdependencies in your application, I think it's really important that load testing tools allow scripting. So K6 allows scripting, and Artillery both allow scripting. There are probably other tools out there that do, but I think it's pretty important to have that in your tool. Thing number 2, contemporary applications load resources dynamically based on browser state, local storage, cookies, service workers, tons of different sort of like things. If you're testing raw, what we call protocol-based HTTP, or protocol-based testing, or just raw HTTP requests, you're probably missing some amount of that sort of like nuance in how requests actually happen on your application. So yeah, traditional load testing doesn't really cover modern web apps. Third point, contrary to expectations, browser-based testing was actually totally doable for something at the scale of New Jersey unemployment. And I would go ahead and venture a guess that it probably works for like 99% of the projects out there. I wouldn't want to test like the Super Bowl website on browsers, but like, you know, like we're not that far off. So yeah, I was really surprised by that. And I think I chalk this up to the fact that for our workflow, we had a lot of waiting, and we had a lot of sort of like we were not going quickly through iterations. If you think of one iteration as like filling out that whole form, it opens a new browser tab for each trip through the form and then closes it at the end. And so the overhead of creating that tab and then closing it is actually relatively small compared to the length of time that it's going to be running that particular workflow. So anyway, do your own homework there, but I was really pleasantly shocked by how much performance we got out of it. AWS code build can scale beyond what I thought. You know, with the right configuration, a very large code build job can do quite a bit. There are certainly circumstances where you would want to parallelize this out to something like Kubernetes or Elastic Container Service, but code build is easy, it's simple. We don't have to worry about reporting results back to like a central location or any of the parallelization sort of like headaches. We have a single instance that's running our tests, and it collects all the data and then reports it back. And then shared object models can encourage consistency and collaboration. So as I talked about those page object models, those are you know, things that we share amongst our end-to-end tests and our load tests. And so that really made it a lot easier to develop. And then for bigger takeaways, you know, obviously the render time is going to be important. What we found during some of our testing, and I don't have great examples of this, but we did find examples of where like a single slow request early in the chain can really lengthen the time that an entire iteration takes. So front-end performance matters. And then finally, test user journeys, not endpoints. I think that's a point I've kind of driven home over the course of this presentation. For us, it really just allowed us to communicate much more effectively about what the impact was of a change, and shifted testing from a purely technical activity to something that we can really talk to stakeholders about. So that's it. I'll take any questions if anybody has them. We have a few minutes anyway. Yeah.
I'm curious, how many applications or teams support the entire system? Is there challenges in maintaining the stability of the site
During
during the load tests?
the load tests?
Just making sure everything's up and running, ready to go prior to the load tests, making sure it's in stable state.
Got it, yeah. Yeah, so we do have, so I think there are 7, 8, 9 Scrum teams working on the project. Like, it's a lot of people. The sort of like DevOps team that we have covers across multiple applications, and so that's the main team that we have to coordinate with. Frankly, there's not a lot of coordination necessary there. Like, they deploy, we have a whole CI pipeline that makes sure that the release is stable and sort of like ready to go. And so we haven't had a ton of issues of like needing collaboration across all those teams to keep things up during load tests. It's kind of.
Let's say there's an issue with one of the services with contact that team, how do you scale up your service?
Oh, okay.
Issues happen.
Okay, sorry. So your question, just to restate, is like, how do you communicate across the teams when there are issues discovered during load testing that need triage, or, yeah, so like a performance issue that we discovered. Yeah. Yep, so typically we're doing load testing as part of the release process, and what will happen is if we discover something during load testing that is concerning, we'll push the pause button on the release until it can be investigated. And that investigation usually frontline involves that DevOps team who's pretty familiar with the applications that are running. And then as a secondary thing, we'll get the application teams involved. So that's sort of the like escalation path there. Yep.
So it seems like you were testing, doing the load testing in a like staging environment.
Yes.
Videos. Yep. Do you do testing in a production environment?
So the question was, do you do load tests? It seemed like we were doing testing in a staging environment, which is correct. Do we do testing in a production environment? And for this application, the answer is no, because we're putting actual data into the application, like submitting that form, and we don't want that data in production. Yeah. Yep.
How much of the parallelism that you need for load testing comes from artillery versus from, I guess, just spinning up a bunch of other jobs?
How much of the parallelism that you would need from load testing comes from artillery versus just spinning up multiple code build jobs? Okay, so parallelism in load testing is pretty simple, actually. It is just spinning up a whole bunch of jobs to run side by side. The complicated part comes when you need to orchestrate getting the results out. So if you spin up container A and container B to run side by side and both generate a certain amount of load, when they finish, you need to sort of like sew those results back together into one cohesive view of here's what the P99 was, here's what the P50 was, et cetera. And so that is something that is handled, like artillery does have tools for that. Again, we don't actually need to use those tools because we're running in a single job, but artillery does have tools for both kicking off in ECS and collecting and aggregating those results back together.
That was totally not the answer I was expecting.
Yeah, yeah.
I think it's more a question about artillery. Also related to your app. Depending on the form that you're filling in, I may assume that you have a different type of form depending on the answer of the user.
Yeah.
And load test, the data sets of load test is super important.
Yeah.
You don't want to have a statistic cache, obviously.
Mm-hmm.
So how does artillery spread the data sets across different containers or browsers? And how do you manage the different forms
Yeah.
the answer of the form of the user?
Okay, so the question was, let me see if I can quickly summarize this. The question is that each trip through that intake form could potentially need different data because as you provide answers in the form, you're going to branch and end up in different places. And so knowing that you're going to need different data for each iteration through, how do you manage that across iterations? Is that
And how,
okay?
how is the data spread out?
And how is the data spread out? Well, again, this is a place where it is fortunate that we are operating on a single instance because there is no spread out here. It is a single command that runs that spins up multiple processes, but like the processes sort of like handle their own intercommunication. Sorry, each process is one iteration. Now, as far as the data, that's a whole topic unto itself, and you're absolutely right. We have a whole bunch of data, and no two iterations can use the same data. And so there is a pool of social security numbers, fake social security numbers that we use during testing, and we pick them up one at a time and never reuse them. And so there's a whole process behind the scenes of managing that pool, making sure that the test is able to pick up sort of the next one. That's not something that's built into Artillery, although Artillery does have some basic tooling for like, you have a CSV and it iterates through that. So I'm happy to talk more about that later, but yeah, I think probably stop there because it is a whole thing. Cool. One more question?
Rob, you touched on SLAs.
Yeah.
Performance. Where did they come from? Is that mighty Acorn, or did the state themselves know what they wanted to achieve?
Yeah, that's a good question. So the SLAs were set out at the like outset of the project, and so we had a pretty easy job there. But yeah, normally we would help to develop those SLAs. Yeah. Cool. Great. Thank you so much, and yeah, feel free to reach out if you have any other questions or come talk after.